Welcome to finding more particular solutions. So in this problem, our job is to take the equation y double prime minus 2y prime plus 5y is equal to 3x squared plus 2x and find a particular solution and then find the general solution. So for a particular solution, we consider that right-hand side. The right side of our equation is 3x squared plus 2x. 3x squared plus 2x, if we want to take a similar form, let's go ahead and start by assuming the y prime is equal to ax squared plus bx. Sorry, not y prime. Y itself is equal to ax squared plus bx, yp. Then we would have yp prime is 2ax plus b. And we would have the second derivative is just 2a. Now, if we plug this in, we would have y double prime, so 2a minus 2 times y prime, so minus 2 times 2ax plus b, and then plus 5y, so plus 5 times ax squared plus bx. And this should all be equal to that 3x squared plus 2x. Now, we have an issue here in that we will likely have a constant term, a linear term, and a quadratic term. So this side over, the left side here will have 3 terms, right? Constant, linear, and quadratic. To match with we could add a plus 0 on the end over here, but we only have 2 constants. And so this may or may not have a solution as it is. So what we actually want to do is scrap what we've done so far and add in an additional term that we need. So we really will need 3 constants. So instead of just doing ax squared plus bx, we're now also going to add that constant term. So starting over, again, we had y double prime minus 2y prime plus 5y is equal to 3x squared plus 2x. Let's go ahead and assume yp is equal to ax squared plus bx plus c. As a general rule, if we have constant coefficients on the left-hand side and a polynomial for a yp, you'll need to pick all of the lower powers as well. So if we have constant coefficients on the left, We don't have that x squared and x to force our terms to continue being x squared. So if we have constant coefficients on the left, then we need to include terms for the lower powers. In YP. So now we're going to redo this and we'll have 3 constants to solve for the coefficients for our 3, or to match the coefficients for our 3 terms. So we have our YP. YP prime will just be 2ax plus b. And the second derivative will just be 2a. So the only thing that's changed from our first attempt to now is that initial YP has the plus c. Then what we get from here, plugging in, we had y double prime, so 2a, minus 2 times y prime, so minus 2 times 2ax plus b, plus 5 times y, so plus 5 times ax squared plus bx plus c. All of this should be equal to that 3x squared plus 2x. This becomes 2a minus 4ax minus 2b plus 5ax squared plus 5bx plus 5c is equal to 3x squared plus 2x. Rearranging these, we have 5ax squared plus negative 4a plus 5b times x plus 2a minus 2b plus 5c. For our constant term, this is all equal to 3x squared plus 2x, and we can do a plus 0 on the end. So matching coefficients, we get that our 5a must match the 3 in front of x squared. Our negative 4a plus 5b must match the plus 2. And then the 2a minus 2b plus 5c must match our plus 0. So again, this gives us 5a is equal to 3. So we immediately know that a is equal to 3/5. We have negative 4a plus 5b is equal to 2. Plugging in our 3/5, this becomes negative 4 times 3/5 plus 5b equals 2. Or negative 12/5 plus 5b equals 2. This becomes 5b is equal to 22/5, or b is equal to 22/25. And then finally, we have 2a minus 2b plus 5c equals 0. So our a was 3/5. We have 2 times 3/5 minus 2 times 22/25 plus 5c equals 0. 2 times 3/5, we're looking at 6/5 minus 44/25 plus 5c equals 0. That becomes negative 14/25 35ths minus 44, 30 25ths minus 44 25ths plus 5c equals 0. And we get that c is equal to 14 125ths. So we didn't need that plus c in order to solve our system where we mashed our coefficients. At this point, we know our particular solution. So we have particular solution, yp is equal to, we had 3/5 for our a, so 3/5 x squared plus 22 25ths x plus 14 125ths. So this is our particular solution. Then we have for our general solution, we first need to find the fundamental set for the homogeneous. So we had y double prime minus 2y prime plus 5y equals 0 for a homogeneous equation. I'm just going to verify that I have that correct. Yes. So from here, this has characteristic equation, r squared minus 2r plus 5 is equal to 0. You can either use quadratic formula, try to factor, it doesn't look like it will factor, or do complete the square. So this is r squared minus 2r plus 1 plus 4. Again, here what I did was I divided by 2 and then square to get the plus 1. And then plus 4 is what's remaining to get our 5. This is equal to 0. So we have r minus 1 squared plus 4 is equal to 0. Or r minus 1 squared is equal to -4. That means r minus 1 should be plus or minus 2i, square rooting both sides. And we get r is equal to 1 plus or minus 2i. I need to give myself just a little more room. From here, we know then that we have our complex conjugate roots. So we get y1 would be e to the 1 times x, or e to the x, times cosine of 2x. And our y2 is e to the x times sine of 2x. Right, this is our u plus or minus iv. And this is e to the ux cosine of vx. And e to the ux sine of vx is where these came from. So we have our particular solution. We have our fundamental set of solutions for the homogeneous equation. Then we have that our general solution should be y is equal to our particular solution, 3/5 x squared plus 22 25ths x plus 14 125ths plus c1 e to the x cosine of 2x plus c2 e to the x sine of 2x. So from here, a little bit useful theorem we have for using this technique we were just working with. Let's consider the equation y double prime plus p of x y prime plus q of x y equals f1 of x plus f2 of x. Then if yp is a solution, let's do yp1 is a solution to y double prime plus p of x y prime plus q of x y equals f1 of x, and yp2 is a solution to y double prime plus p of x y prime plus q of x y equals f2 of x. So if we have a solution to the non-homogeneous just working with f1 on the right and the non-homogeneous just working with f2 on the right, if we have a solution to both of those, then if we take yp equal to yp1 plus yp2, this is a solution to the original equation. So a reason this is helpful, if we are sort of trying to guess our coefficients for similar right-hand equations, we can break it into parts. So if, say, we had a e to the 3x plus a constant, we could work with just the e to the 3x first, and then we could work with a constant separately. So this allows us to sort of break a problem into pieces. So just a quick warning. This method of guessing coefficients will not always work matching the right-hand side. So this method of matching the right-hand side, or of guessing that yp is similar to the right-hand side, will not always work. So for a quick example, let's take the equation y double prime minus 4y prime plus 3y equals e to the 3x. Okay. So we will assume yp is equal to some constant a times e to the 3x. Then we have yp prime is 3a e to the 3x, and yp double prime is 9a e to the 3x. And plugging in, we have y double prime, so 9a e to the 3x minus 4 times y prime, so 4 times 3a e to the 3x plus 3 times a e to the 3x equals e to the 3x. The left-hand side simplifies to 9 minus 12 plus 3 times a e to the 3x. Setting this equal to e to the 3x, this becomes 0 equals e to the 3x. So we have a problem. The problem here is that that right-hand side is actually a solution to the corresponding homogeneous equation. So the problem is the right-hand side e to the 3x is actually a solution to the corresponding homogeneous equation. Next week, we will learn how to deal with this. We will learn how to deal with this in sections 5.4 and 5.5. But this is a potential sort of technique for finding particular solutions to non-homogeneous equations and solving them. It's not the only technique available to us, but it is one possibility.